Okay, so today we're going to talk about operating system support. If you have the 10th edition of the textbook, this is in chapter 8, and we're going to cover the first part of it in this presentation. So an operating system is a program that controls the execution of application programs and acts as an interface between the applications and the computer hardware. There are two objectives for an operating system to have. One is convenient, to make the computer more convenient to use for the end user, and the other is efficiency, which basically is to allow us to more efficiently utilize computer system resources. And, in some ways we want to abstract the detail of the hardware from the programmer and provide them with a convenient interface for using the system. So operating systems should help out with several different services. One is program creation, things like your notepad for putting together a program, or integrated development environments such as C-Line or Visual Studio. Should help out with program execution. If you double click on something in a GUI, you should be able to run it. And the operating system is the thing that will take control of running that for you. Access to I/O devices, your printer, your mouse, your monitor. Basically, it should take care of the details for how those work so you can focus on what you actually need to do. And then controlled access to files. Basically manage the disk for you so you know where to find your files, and if you want to open something and edit it, you should be able to do that. It should control access to the system as a whole and to specific system resources, particularly when it's shared or a public system. It should also be able to manage different types of errors for you and clear error conditions with the least impact on running applications. In other words, it shouldn't always do a core dump as a response to a runtime error. And it should collect usage statistics for various resources and monitor performance parameters such as response time, memory utilization, etc. So three key interfaces in a computer system. One is the instruction set architecture. We're going to talk about that a little bit later in the text, but these are basically the machine language instructions that a computer can follow. And that forms the boundary between the hardware and the software. There's the application binary interface that defines the standard for binary portability across the different programs, and the API itself, which gives the program access to the hardware resources and services available in the system through the user instruction set architecture, supplemented with the high-level language library calls. The OS should also manage resources and act as a control mechanism. So a couple interesting things. One thing is the operating system is actually a program, even though it's managing other programs. And so it needs to function in the same way that a program operates, but it also needs to relinquish control and run other programs. And it has to rely upon the processor to allow it to regain control. So there are two types of operating systems. One are interactive systems. That's where you interact directly with the computer to request the execution of a job or to perform a transaction. These are things like your Windows or Linux desktops. And you may communicate with the computer during the execution of the job. The other one is a batch system, which is very much the opposite of interactive. You batch together the programs from other users and submit them via a computer operator. After the program's completed, the results are printed out for the user and they hand them back for you. That's very much the old school version. Another way of categorizing operating systems are uniprogramming versus multiprogramming. And this specifies whether it employs multiprogramming or not. With multiprogramming, the attempt is made to keep the processor as busy as possible by having him work on more than one program at a time. Uniprogramming, you only have one program active at a time. We'll see some of the drawbacks to uniprogramming. So a bit of history. The early systems in the 1940s and 1950s, like the Colossus and the ENIAC that you saw in the museum assignment, the programmer interacted directly with the computer hardware. There wasn't an operating system, and you might have had to actually rewire them directly, as in the case of the ENIAC. Here we see the IAS, and there was a bit more interactivity in that one, but still not much compared with our modern systems. And when you take a look at like the Altair, the processors were run from a console consisting of display lights, toggle switches, and some form of input device, and perhaps a printer as an output device. So early systems had problems. One was scheduling, and basically back in the day when my father was studying computer science, you had sign-up sheets that were used to reserve processor time. And so these, you would go into the computing center or the building that housed the computer, and you would take down the clipboard and sign up for processor time. And somebody didn't sign up for a particular block, then you had idle time, or if the program finished early, terminated due to an error, then that block was reserved and nothing else was going on. You definitely had wasted time. The other thing is there was a setup time, which was loading the compiler plus the source program into memory, saving the compile program, loading and linking together the object program and common functions were required. So we introduced a couple different things. One was the monitor, and this was a simple batch operating system. The user submitted jobs on cards or tapes to the computer operator. They batched the programs together. They put the batch on an input device for use by the monitor, and the monitor was always in main. So this was a very early operating system. It read in one job at a time and passed processor control to that job. The processor executes, from the processor's point of view, it executes instructions from the portion of main memory containing the monitor. Those may transfer over to a user submitted program. And the monitor handled setup and scheduling using what was known as a job control language. Monitor batch OS is just a program at the end of the day, but it's a very important program. So let's look at this job control language. And here you can see the job control language ones are set off by a $sign. So the first one is job, which tells us we're starting a job. The next one is FTM, which is Fortran. We would get some Fortran instructions to run some type of program. We would load those into the memory, run it. We would get some data from it, hopefully. It is Fortran after all. And then we would end it and pass control back to the monitor. So the job control language is the ones with the $signs, and the two arrows indicate the things that we're actually programming. Some desirable hardware features with operating systems. One is memory protection. Program shouldn't alter the memory area contained in the monitor. The processor hardware should detect error and transfer control to the monitor if that happens, and have the monitor abort the job, print an error message, and load the next job. The other one is a timer, which is used to prevent the job from monopolizing the system. The timer expires, an interrupt occurs, and returns control to the monitor. So if you're trying to do too long of a calculation and it would end up eating up all the time from somebody else, then the timer goes off and have to terminate your program. There were other things like privileged instructions, which can only be executed by the monitor. If the processor encounters an instruction that's a privileged instruction while executing a user program, they give you an error interrupt. I/O instructions are privileged, so the monitor maintains control of all the I/O devices. And interrupts is another desirable hardware feature that gives the OS more flexibility in relinquishing control and regaining control from user programs. So processor time alternates between the execution of the user program and the execution of the monitor. There are two sacrifices with having the monitor there. Some main memory is now given over to the monitor. Some processor time is also consumed by the monitor. And both of these are forms of overhead. But even with that overhead, just the simple monitor batch system improves the utilization of the computer. So even with automatic job sequencing provided by a simple batch OS, the processor would still often be idle. And the problem is the IO is slow compared to the processor. So here's an example of a program reading one record from a file 15 microseconds, executing 100 instructions 1 microsecond. That's much quicker to run commands than to read and write. Writing one record to a file 15 microseconds. So it takes a total of 31. But the CPU was only busy for 1 out of 31, or generously, if we want to say, the read and write were one instruction, that'd be 3 out of 31. It's still only 10% of the time. So we're not making good use of the CPU there. Another technique is, so that's a unit programming environment. Multi-programming environment is where we have multiple things running. So the processor spends a certain amount of time executing until it reaches an IO instruction, and then has to wait until the IO instruction concludes before proceeding. And we know there needs to be enough memory to hold the resident monitor and the single user program. Suppose there's room for the OS and 2 programs. We could even expand it to hold multiple programs. Now, when one job needs to wait for IO, the processor can say, okay, hey, you're waiting for IO. That's going to be a while to read out to that file or write to a tape or print something or get input from a user. While you're waiting for that, I'm going to switch over and execute the other program. So multi-programming allows you to, in some ways, interleave these jobs. So imagine we have these 3 programs submitted. Job 1 is heavy compute. Jobs 2 and 3 are really focused on IO and don't require much in the way of the processor. If we execute them in serial, then we take 5 plus 15 plus 10 minutes, which would be 30 minutes to execute them. But if we are able to interleave them in multi-programming, because there's little contention between those jobs, all 3 can run in nearly the minimum time. Job 1 still requires 5 minutes, but at the end of that time, job 2 will be 1/3 finished and job 3 will be half finished. And so all jobs can finish up within 15 or 20 minutes. And in fact, this example data shows that they all finish up within 15 minutes, and the throughput is twice as high. The mean response time is nearly 1/2, and we're making much better use of the memory of the disk and the printer. You can extend the benefits of multi-programming by incorporating IO interrupts and direct memory access that we saw in the previous chapter. And of course, those require memory management. The next evolution was time-sharing systems. And batch programming doesn't allow for interactivity. You're not necessarily giving input, you're giving input based on data that was on some of the later cards. The time-sharing system offered a solution. The processor's time was shared among multiple users, but everybody thought that they were the only person on the computer. Multiple users would simultaneously access the system through terminals, with the OS interleaving the execution of each user program in a short burst or a quantum of computation. If there were end users actively requesting service at one time, then each would see on average 1/n of the effective computer speed, but it was still like you had your very own computer. And pictured here is the University of Michigan Computing System, Computer Center MTS, Michigan Terminal System, which was a multi-programming environment. And there are some key differences. With the, the MTS was time sharing. With time sharing, you focused on minimizing the response time and you had user commands entered at the terminal. With batch multi-programming, you're interested in maximizing the processor use, and you use the job control commands provided with the jobs. As an aside, in 1971 at the University of Hawaii, Professor Norman Abramson was funded by DARPA to link Hawaii to ARPANET, which was the early internet. And they did this through the BBC 500, which could accommodate 500 simultaneous users and over 2,000 terminals. And this was free to use, so they didn't actually charge you like a lot of the other states did. So another major thing the operating system needs to do is scheduling, and the key to multi-programming is the scheduling. In order to understand scheduling, it's important to understand what a process is. And there are three different definitions. One is a program and execution. The other, which is a favorite of mine, is the animated spirit of a program. And the entity to which a processor is assigned is the third definition. And so there are four types of scheduling. One is long-term, which is the decision to add to the pool of processes to be executed. Medium-term scheduling is the decision to add to the number of processes that are partially or fully in main memory. And short-term scheduling is the decision as to which available process will be executed by the processor. And of course, IO scheduling has its own type of scheduling. So long-term scheduling, we determine which programs are submitted for processing. Once submitted, a job becomes a process for the short-term scheduler. In some systems, the newly created process begins in swapped out condition, in which case it's added to the queue for the medium-term scheduler. The batch system has newly submitted jobs routed to the disk and held in the batch queue. The long-term scheduler creates processes from the queue when it can. And then for a time-sharing system, the processor request is generated when a user attempts to connect to the system. The OS will accept all authorized covers until the system is saturated, until you basically have more users than you can handle. And at that point, a connection request is met with a message indicating the system is full and to try again later. Actually had that error. I'm old enough to remember that one. Medium-term scheduling is part of the swapping function, and swapping in is based on need to manage the degree of multi-programming. Consider memory requirements of the swapped out process, and we'll cover this in the next presentation. Short-term is known as the dispatcher. It makes the decisions whether or not to take on a new process and which one to take on. And the scheduler executes the most frequently between the short, the medium, and long term. And so there are 5 defined states for a process. One is new. This one's newly admitted by the high-level scheduler, but it's not yet ready to execute. Ready, it's ready to execute and it's waiting access to the processor. Running, it's currently being executed. Waiting, it's suspended from execution, waiting for some system resource, usually IO. And then halted, the program process is terminated and will be destroyed by the OS. So here's what the process model looks like. You get a new process, it gets admitted, and then it becomes in the ready state. The dispatcher sends it to the processor where it's running. If it has a timeout, it goes back to ready. If there's an event wait, such as IO, then it goes as blocked or waiting. And if an event occurs and unblocks it, it goes to ready, and then it can get access to the processor again. After it's done, it gets released and it's allowed to exit. So to do all this effectively, you need to know the state of the process. And this is done via the process control block. Now, most of the things that get recorded in this process control block are pretty clear. The memory pointers indicate the start and end locations of the process. Context data relate to what is in the register, so you need to obviously save that if you're going to share things back and forth. And accounting information concerns the amount of processor time and clock use, time limits. Are you using too many system resources? So here's an example, and this shows how main memory is partitioned at a given point in time. The kernel or the operating system is always resident, of course, or your monitor. In addition, there are a number of active processes, and here we have A and B, and there are some other partitions down at the bottom. We begin at a point in time where process A is running. The processor is executing instructions from the program contained in A's memory partition, and at some point we cease to execute those instructions. It may be an interrupt or something that makes A go into a waiting state. In that case, we transfer control to the operating system. The processor will save the current context data and the program in A's process control block, and then begin executing the OS. When the OS is done with its work, the scheduler, the short-term scheduler, picks what goes next. In this case, it may be process B that's selected, which we can see in part C in this scheduling example. Some key elements of operating systems for multi-programming. The major elements of the OS involved in multi-programming and scheduling of processes. The OS receives control of the process if the service call or interrupt occurs. There's also 3 queues. There's the long-term, short-term, and IO queues. And you can see the interrupt handler and service call and handler code. And that's it. Thanks so much for watching.